I'm a new PhD student from Aalto University, and I'm here today to discuss my results of my master's thesis of numerical study on the effects of heated channel walls on the premixed methane combustion dynamics. My supervisor is Vili-Petteri and co-advisors Mahmoud Kadalla, Professor Ossi. So, as we all know, when we have cold walls and flame reaches it, it usually quenches. And this can lead to fuel leak, and this, of course, wastes fuel, which is costing us money, and also creates emissions. However, if we have a hot wall, the flame is able to reach the flame, and in those cases, usually all the fuel is burned, and no fuel slip is seen. This, of course, increases efficiency and the emissions are decreased. This is especially important in small, narrow combustions where we have, let's say, micro and mesoscale, because in those cases we have a very large wall-to-volume ratio. And where these kind of mini combustors are used, they can be used in, for instance, in small unmanned vehicles, flying vehicles in space, and anywhere where we want to carry the fuel and use it. This is very good over, let's say, batteries, because when we carry fuel, we have a very high energy concentration over the mass. So what was my objectives? I wanted to see if I can ignite the fuel with hot walls in the channel. I wanted to investigate the combustion dynamics, and also add in the channel vortex generators to increase the heat transfer and see how this would affect the combustion dynamics. Here you can see a schematic flame, V-shaped flame in the channel from literature, and here is my simulation results, and we can see that it matches very well. So basically we have an attachment point, we have the flame front, and on the left we have the fuel, and on the right we have the burnt products. I was supposed to have an animation, but unfortunately it doesn't work, but you can imagine it's very cool. Here is my simulation domain. It's a 2D channel. On both walls, top and bottom, I have an isothermic boundary condition, so I keep cold temperature at the beginning and then increase it to a higher temperature, and this will heat the mixture and ignite it hopefully. From the inlet, I keep already a parabolic inlet velocity to not have to involve the boundary layer itself. Here you can see also the boundary conditions and initial conditions, but basically we work in atmospheric pressure, and we have stoichiometric methane air mixture. On the right we have 3 different domains: an empty channel, then 2 domains with either 1 or 2 sets of vortex generators, and this vortex generator type is from our Vili-Petteri's own paper, unpublished paper, where he studied which configuration would be the best for heat transfer from the hot walls into the mixture. And as also discussed here many times, I used DLP foam together with Bijak and Labak and GRI3 chemistry mechanism. And the cell size is homogeneous, 20 by 20 micrometers, which is roughly 20 cells per flame thickness. Next, you can see the simulation matrix. So what I varied is the hot wall temperature, and also in one case, after the flame had established, I took away the heating to see how the flame would behave in those cases. Also, in the coldest case, I added VGs to see how they would help, and also varied the channel height from 10 millimeters to 1 millimeter. So next I will go through the results quickly to show you. So here I varied the wall here. And from the V-shaped flame I took away the heating, and as we can see, that leads to some instabilities which will break the symmetry and make the flame unstable, and it will eventually move towards the inlet itself. And also we can see that the flame quenching is much higher in this case. Next, I varied the channel height, 1 mm and 10 mm. In 1 mm case, ignition occurs much faster, and also we can see that the flame itself is unsymmetric from the get-go, and eventually after, in this case, 100 milliseconds will lead to a oscillating flame, and the oscillation is very stable itself. Finally, I added these vortex generators in the domain, and at least in this particular case, of course it depends on the Reynolds number that we work with, but as I kept the inlet velocity constant throughout all the simulations, in this case the inlet velocity is a bit too small to really harness the potential of these VGs. So in one case of one set of VGs, we can see that the ignition actually is pretty much, the IDT is pretty much the same as without any VGs. But in case of two, we have higher vorticity, and this actually decreases the IDT about 20% in this case. However, after this study, I did some other simulations just to find out more about these VGs, and what I found was that actually in many cases, even though the vorticity and mixing is increased, and it will increase the mean temperature of the mixture, it can easily postpone to ignition, because for ignition we usually need this one hot spot where the heat has gathered, and that will ignite the whole mixture. But with very good effective mixing, we don't have that, and that can actually postpone the ignition. So, to quickly conclude, if we vary the channel height, well, in this case, in this Reynolds regime, decreasing the channel height lead to a unstable asymmetric flames, but this is because bifurcations in the system. Unfortunately, due to time and resources, I was not able to dig deeper into these bifurcations, because it would require much more simulation. But as shown by other groups like Maruda's group in Tohoku University in Japan, or Ulus and Pizza in Switzerland, they have studied this much further and seen similar things. Then wall temperature itself, of course the IDT changes, but eventually it all leads to similar shaped flames. Wall cooling breaks the symmetry, and VGs have a slight advantage in this particular case for the IDT, but as I said, can also postpone the ignition itself. For the future, what can be done? Of course, these are only a couple of test cases. A thorough parameter speed should be done, but that is very expensive and something we don't currently have possibility to do. Also, we could include complex thermochemistry, use alternate fuels like methane. Instead of methane, we could have hydrogen, ammonia, whatever. And we can also consider turbulent cases, move from 2D to 3D, and also, as there exist many instabilities in these kind of cases affecting the flame dynamics, these are not all simulated here, and they could be simulated further. So, thank you very much for your attention, and hopefully we can soon go to eat. If you have any questions, please